Hey people, now we are going to talk about energy changes when it comes to changing states of matter. So we're going to incorporate what we learned in the last chapter when we were talking about phase changes, like melting, um, when we were talking about uh, freezing, when we're talking about boiling or vaporizing, condensation, things like deposition or sublimation, things like that. When you have a phase change, there is no temperature change. So we cannot use the Q equals MC delta T equation. But does that mean that it takes no energy? No, of course not. We're just going to have to use a different equation. Okay, we can't use this equation because on a graph, we end up seeing that there is that plateau. So this is something that we went over last chapter in chapter 10. And we saw that that plateau means that the delta T would be 0 degrees, and anything times 0 is 0. So we have to have a different type of equation for those phase changes. All right, so this is where we are going to talk about the heat or enthalpy of a reaction. This occurs during those phase changes where the temps are constant, where we see our plateaus on our graph. So here you see the heating curve of H2O again. All right, solid H2O is going to be our ice, all tightly packed together here. Liquid H2O is going to be our water, and gaseous H2O is going to be our steam. Okay, the temperatures here on the y-axis. Okay, it's going to freeze at 0 degrees Celsius, and it is going to boil at 100 degrees Celsius. And we see the freezing and melting, condensing, boiling constants, our plateaus right here. Okay, so we have to use a different equation here on these different flat parts of the graph versus on, say, this part of the graph or this part or this part where there is a delta T. So these three parts, I can use that Q equals mc delta T equation. So we're going to use the heat of the reactions on the plateaus. So the heat of the reactions are going to be a constant, and we're basically going to use algebra, a type of dimensional analysis, in order to figure that out. So this is going to be our heat of fusion, heat of solidification, heat of vaporization, heat of condensation, and when we dissolve stuff, heats of solution. So again, remember, heat is delta H for enthalpy, and that means how much energy it takes. Okay, so fusion is probably the one that you end up um, not knowing intuitively enough on your own. This is going to be when stuff melts. Okay, solidification is going to be when it freezes. Vaporization is going to be when it boils, and condensation is when it condenses. That one's really obvious. And solution is going to be when things dissolve. Okay, so let's go over these values. Excuse me. The molar heat of fusion is the amount of heat absorbed when 1 mole, hey moly moly, of a substance moves from a solid to a liquid at a constant temperature. So this is, like I said, melting. I'm going to go over all of these constants for water. They are different for different substances. So the delta H of fusion for water is 6.01 kilojoules per mole. You can multiply by 1,000 joules per kilojoule, and you can multiply by um, 4.184 joules for a, or I'm sorry, not 4.184. My bad, my bad. Back up here, back up here. And then you can do your 18.01 18.02 grams of water per 1 mole, which is our molar mass. And you can use them in these units also, 333.3 joules per gram. This is going to be the one that we're going to use most, okay? So if that's how much energy it takes to melt, how much energy does it take to freeze? You got it. The exact opposite amount. Okay, so for the heat of solidification, this is when you are going to see things freeze, and you're going to see that this is a negative value, negative 6.01 kilojoules per mole, or negative 333.3 joules per gram. Okay, for vaporization, this is how much energy it takes to boil, okay, to go from your 1 mole of water to 1 mole of your steam. That is 40.7 kilojoules per mole, or 2,256.9 joules per gram. So what would condensation be? Condensation would be the exact opposite. So it would be the negative 40.7 and the negative 2,256.9 joules per gram. All right, so this ends up helping you see the differences between our parts. Now, when it comes to the molar heat of solution, when something is going to dissolve, this depends, is it going to be exo or endo? So the constants will vary with the substances that you are dissolving. When ammonium nitrate is going to dissolve, it is going to be a positive value. It's going to feel cold. That's what's in our instant ice packs. But if you have calcium chloride or something like that, it is going to be negative, and you're going to see that it's going to feel hot. Okay, so the grand all be all equation that we use is going to be this. Okay, the Q is equal to the mass times the delta H of the reaction. Okay, M is a general term for amount. We are going to use it in terms of mass because we're going to use our delta H values in joules per gram. So if this is in grams and we're multiplying by joules per grams, you will see that your grams and your grams are going to cancel out, leaving your joules at your final unit. Okay, so let's do a sample problem. Go grab a calculator, come back, push pause if you need to. Hey, you're back. All right, so how much energy does it take to boil 29.0 grams of water at 100 degrees Celsius? You'll notice, pro tip, okay, you'll notice there is no second temperature. So if you don't see a second temperature, there is no delta T. So you have to use the Q equals M times delta H of reaction equation. So what are we doing here? We are going to boil. So that means we are doing Q equals M delta H of vaporization. Okay, 29 grams is going to be our mass. Okay, boiling, we have our delta H of vaporization, which is going to be 254.6. And we are going to see that we plug everything in and get our calculations. So we have 29 grams times our 2254.6 joules per gram. And we are going to cancel out grams. In my calculator, I get 65,450.1 joules. That's a pretty big number. Okay, so if you have something over 1,000, we are going to move the decimal place over 3 times and report in kilojoules. It is the polite way to do this. All right, so we end up saying, oh, I'm sorry, on the previous slide I said it was 2254. It is 2256. Okay, joules per gram. So we end up getting our answer and we round to 65.5 kilojoules. All right, and that is how you solve a delta H of reaction equation.